When we take inductors and introduce them into circuit applications, we're going to find a very similar solution to the time evolution of those circuits as we found with the RC when we placed capacitors into series with resistance. In all of our discussions, our ideal inductors are going to have no resistance of their own. That's usually a decent assumption as long as your external resistance in the RL circuit is large. The resistance that is inherent in the wire wrapped around the core of the inductor will be negligible. So if we write down a KVL loop rule around our battery resistor and inductor circuit, we have a plus battery voltage V. If we travel with the battery clockwise, we come up to minus the current I times the resistance R, and minus L di dt. You'll see in class where this relationship comes from. It tells us the voltage drop across an inductor, and the Lenz's law aspect here is that the direction of the current is not important. To find the voltage drop across an inductor, all you need to know is how the current is changing with time. Right away you can see the differential equation nature popping up. We finish the loop, come back around to where we started, and set everything equal to 0. So we have an expression that contains both current and the time derivative of current. If we rearrange things, you can talk about the limits, the limiting behavior, as we'll do in class. When time is 0, the inductor abhors change, right? Kami Santa abhors change. The inductor will push back against the attempt of the battery to push current through the circuit. So if that starting current is 0, your initial di dt, the rate of change of the current, will be given by the voltage divided by the inductance. After a long time has elapsed, the inductor will lose its battle pushing against that current, and a steady state current will be developed. You will have DC current flowing clockwise around the circuit. Di dt will be 0 in that case, and you can then solve for the steady state value of the circuit current, which is just V over R. It is as you would expect if the inductor were a short. It's acting as a wire when you have steady state current, and it acts as an open in the case where current is rapidly changing in that first instance when you close the switch. Just like we did with the RC circuit, you can separate the differential equation and integrate both sides. We don't need to think about the details of this. We'll give you the current as a function of time is that steady state current, V over R, times 1 minus exponential decay, e to the minus R divided by L times t. So that looks like your I infinity, 1 minus e to the minus t over tau. What does this remind you of? It looks like the charge as a function of time in an RC circuit. If it begins uncharged and it's charging over time, it will ramp up to some steady state, or Q infinity we called it, effectively charged state. We don't call this process a charging inductor, we'll call it an energizing inductor. We are increasing the energy stored inside of it, but it's not accumulating charge, it's in a sense, it's accumulating current in its coils, which gives you ultimately a steady state magnetic field inside the inductor volume. The time constant here, you should be careful, is not R times L, it is L divided by R. You'll recall that L has units of ohms times seconds, that's a Henry. Dividing a Henry by an ohm gives you seconds for your time constant. The shape of this graph in blue, current versus time, again in that initial instant, the inductor pushes against the current. It starts to lose that battle and current ramps up to its steady state value of V over R. After one time constant elapses, you are up to about 63% of the steady state current. That's 1 over 1 minus E. In the fully energized state, you will have stored a total potential energy of 1/2 L inductance times the steady state current I infinity squared. The voltage across the inductor starts out high. Remember, it's an open circuit. Starts out high and decays exponentially down to 0. You start out with all of the battery voltage across the inductor, and it will decay down to 0 as the inductor permits a steady state current to develop. It acts just like a wire. You can take the same RL circuit, remove the battery, the voltage source, and reconnect the closed loop. A quick loop rule application gives you another separable first order differential equation, and its solution says that if we have current built up in the inductor, it's going to de-energize over time. It will lose its energy to ohmic heating in the resistor, and the current will decay exponentially. If you did come straight from the energizing circuit and you had already built up I infinity in the inductor, this is your starting value I0 in the de-energizing circuit. So for current, we start up at a high V over R value that was already present at time equals 0. It decays exponentially, so after one time constant, you're down to roughly 37% of the starting current, or 1 over E of I0. The voltage across the inductor, I've indicated switches signs here. We'll see that in class. Again, a voltage will have been established in that first instance, that first moment in time. You'll have a large negative voltage to preserve the loop rule, right? Whatever voltage is across the resistor, you have to have the opposite voltage across the inductor. So we'll start out with a large negative value of voltage and decay up to 0. And again, keep in mind here, the energy that was stored inside the magnetic field of the inductor coils is being spent as ohmic heating in the resistor.